This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, so we'll make a start. I'll go through the lecture quickly, then I'll give you a brief about the assignment, talk about the assignment, and then we'll talk about what is happening moving forward. Any questions from yesterday? You all happy? Was that too much to teach in 2 hours? That's okay, there is some difficult facts that is coming up, so we've got pre-stress concrete to cover, slightly difficult as well. And then we've also got composite construction coming up, so there is quite a few, not difficult, interesting, challenging. That's the right word, okay? So we'll try to make it as simple as possible, where possible. If it's not possible, we'll try to see. Oh my God, this is dead. Oh, okay. So today I'm continuing from where we looked at yesterday. What we looked at yesterday, we're going to continue where we left off. We'll basically talk about all the elements in a portal frame structure yesterday. We'll look at how they behave when we have different wind impacting our structures, industrial structures. We look at the terrain categories, where they're built, what influences their performance. And then today we're going to look at more of, how would I say, more of how the design is being put together and how the structure itself works as one when you have wind. So we'll look at the bending moment distribution, how that impacts our structure, and why we have certain elements the way they are in an industrial frame structure. Any questions? You all happy? So today is much more easier than yesterday, I would think. Okay, so we've got all the references there, and all of these actually is in your reader. And I think I mentioned to you from week 1, please make sure you try to read the reader as you go along. So the readers are meant to supplement the lectures, and they are meant to provide a lot more explanation. So don't keep them till week 12, otherwise you're going to fail. I have to be honest. So the readers are meant to be read. They are not meant there for you to just look at. It's meant for you to be read. Sorry? You don't memorize. You can't memorize in construction. There are so many things. You just read and understand the fundamentals. You cannot memorize that. 500 pages. Okay. So I think I spoke about the loads yesterday. So these are the different loads which we looked at. So I'm going to look at more loads today. Yesterday we talked about dead and live load, which is the general load. We also have what we refer to as a crosswind load and the longitudinal wind load. And then I spoke as well about internal pressure. Is that correct? I spoke about internal pressure yesterday. Remember that? So you have wind coming in, pushes the structure outwards and upwards. That's internal pressure. I spoke about suction. So you have windward wind, which is the wind that blows against the structure, and that's the windward. And then it goes on the other side. It's called a leeward wind. That is something you should have learned in materials and structures. I'm not going to go over that. So what I'm considering today here is what we refer to as crosswind and longitudinal wind, which is different from what you've learned before. Okay? So as what you've done with your assignment 1 and as what you would have done in materials and structures, you do load combination, is it? You use dead load and live load. Do you remember that? So it's the same combination as well we have. So for an industrial structures, we've got these combinations to consider. So you can add dead and live load, dead load, crosswind and internal pressure, dead load, crosswind and internal suction, dead load, longitudinal wind and internal pressure. So you look at all these load combinations. The essence of doing that is when, as an engineer designing a structure in the office, what you want to design for is the worst case scenario. So to make sure you come up with the optimum design which will satisfy every scenario, you have to consider the worst case. So that is the reason why you have to mix and match all these load combinations. So that's the essence why we have load combination. So the worst case represents the governed design, in other words. Okay? So when you have I think I explained this yesterday, when you have an industrial structure, usually it's a rectangular shape. Usually it's about 1:3 or 1:4 ratio, where that might be 50 meters and this might be 200 meters. So along the longer direction, I explained that side of the facade or the cladding will attract more wind because it's got a lot more larger area. Is that correct? Remember that yesterday? So based on that side, which is the bigger area, at 0 degrees is the most critical one. So that wind that blows in that direction is referred to as the crosswind. Okay? And the wind that blows at 90 degrees across the width of the structure is referred to as the longitudinal wind. Does that make sense? So that's the two different winds that impact an industrial structure. So in addition to dead load and live load, we then have to consider crosswind and longitudinal wind when the building is closed. And we also have to consider dead load, live load, crosswind, longitudinal wind, and internal pressure when the building is operating, when it's open, because you have internal pressure sucked in. Is that correct? Remember that? So that's the fundamental. So that's what the representative is. We look at how this load plus the dead and live loads, considering the different load combinations, influences the building behavior. And based on that, we then come up with the design that actually is representative of that particular structure. Okay? So what we're looking at here, this is just an example. As with every design, you have to consider two cases. What are the two cases you consider when you do the design? You design for strength. What's the other one? Another S. Strength and what? Sorry? Serviceability. Remember that? Serviceability. So serviceability basically just has to ensure that the building performs satisfactorily under its service loads. So it means we just consider the ability of the deflection ability of the structure, whereas strength has to deal with how much load it can take until it yields, up to the yield load. Does that make sense? So that's the difference. So we are looking at here an example. We've got a load case. We've got dead load. So dead load is the first one, crosswind, longitudinal wind, internal pressure. Okay? Now, what we're seeing here, this is just an example. We've got a calculated load. Based on the calculated load, we're considering this. We look at dead load is 12.8 kilonewtons, which is 1.28 tons. Crosswind is 82.2. Longitudinal load wind, is 73.2, and so internal pressure is negative. So you can see that when you have, oh gosh, I forgot my tissue box. I want to bring my tissue box to explain this. Anyone with a tissue box here? Anyone with a cold? No one here. I left the tissue box, sorry. Look at the tissue box, small tissue box. Okay? So what happens is, if you have a dead load, so assuming that's a dead load, that is providing gravity downwards. Is that correct? Whereas if you have a crosswind load, it's going to tend to push the structure over. Is that correct? Longitudinal wind is going to push the structure over as well. Internal pressure as well, when the building is open, wind comes in, is going to push the structure over as well. That's why all of them is negative, if that makes sense. Is that correct? Can you imagine that? So all of those loads has to be resisted by gravity. That is why it is the only one that is positive in that case when you consider the vertical position of the building. Okay? Thank you for that. No flow on that, right? That tissue you gave me. So when you look at that, what we then look at, the most important when you have a wind load on a structure, the most or the worst case that could happen is what we refer to as overturning of that structure. So what that means is, if you have wind blowing on a structure, the best thing that could happen is the wind will push over the structure and it will overturn. So in that case, what we refer to it as an uplift. Does that make sense? Uplift, U-P-L-I-F-T, that's what, it's not something different. Does that make sense? So when wind blows, as I explained with the vehicle yesterday, what will happen, and that is what is happening, like what is happening in the US at the moment, when they have the cyclone, you have a lot of wind coming, blowing, and it just topples the structure over. And that can happen in reality. So what we have to do, based on what, experience and a lot of design being done, the most critical load because of wind in this particular structure, because of the height is closer to the ground, what will happen is, the worst case that could happen is the wind will just push it over and push it from the foundation and sort of overturn it. So that becomes the design criteria in which we say it's the uplift case that we use to design what the integrity of the structure satisfies. So to design that, or to calculate that uplift, what you do is you consider all the negative load against the positive load. Is that correct? So if I use myself as an example, if I'm walking into wind, or wind is blowing and I'm standing, wind blows against me, to push me over backwards. Or if it's blowing from my back, push me forwards. And the only thing that keeps me standing is the weight of my body. Is that correct? So the weight of my body is the same as the weight of the structure, which is the dead load, because it's there, it's part of the structure. That becomes the dead load. So that is the only thing that is providing resistance against uplift. So to calculate that, what we do when you have wind, to calculate the uplift load, you consider one case at a time. So you have crosswind. So crosswind and longitudinal wind cannot happen at the same time. So it's one or the other, because the structure is at 90 degrees. Although sometimes you have wind coming from that corner, okay? But usually when you have wind coming from that corner, from statics, that itself resolves into X and Y loads. Is that correct? So it's the same concept. So in this case, what you can see, longitudinal wind is 73, but crosswind is bigger, it's 82. So which means crosswind is the most critical one. And that is evident because the crosswind load, the crosswind of the building has got a bigger area. So it will attract more wind. Is that right? Okay, basically. Oh, sorry. So if you add the crosswind load, which is that, plus the internal pressure, because when you have crosswind, assuming the building is open, because that will be the worst case, when wind comes in, that wind will come in and create internal pressure. So all of those two will be negative loads on the building. Crosswind, internal pressure will be negative. So those two, okay, against the dead load, which is negative in this case, so it is plus, negative, negative. It's just the other way around. So usually those two, the crosswind and internal pressure, is usually factored against the dead load. And then that gives you what the overturning force will be. So in this case, if you remember what you do for your assignment, you multiply 1.2 by G. Is that correct? And 1.5 by Q. Is that right? It's the same thing here. Usually, we multiplied the crosswind and the internal pressure by 1.4, and then you less the dead load, because the dead load is the resistance to the crosswind load. That gives you the equivalent overturning force to push that building over. Why that is important? Because that tells you how much precast panel or how much weight you have to put on that side to prevent the building from pushing over. That's why that is important. So based on that, 11.8 tons, we then can estimate that we need minimum 5 meter cube of concrete on that crosswind side to ensure that when wind blows, that side doesn't lift off and push the building over. Is that making sense, guys? So that's the concept. So how did we get 11.8 tons to be 5 meter cube? Anybody? Yes, sir. So 1 meter cube is 2.5 tons. Do we agree? Not 2.5, 2.4 tons. Do we agree? Anybody who disagree with that? 1 meter cube of concrete multiplied by 2400, which is the weight density of concrete, that gives you 2400 kilograms. Is that right? So 2400 kilograms is 2.4 tons. So 2.4 tons. So if you have 11.8 tons, so 11.118 kilonewtons is 11.8 tons, and then that gives you, divide by 2.4, you'll get about 5 meter cube. That's how we get that figure. Okay, so that's the basis of how we design the ultimate load. No one is going to ask you this, but as I said, why this is very important for some of you guys. Some of you might end up be working for a D&C contractor who only does these industrial structures, and you need to understand how this is done. And as I said to you yesterday, one of your colleagues from last year is now working for Construct, who only does these buildings, and he's doing all of these in the office. Okay? So generally, for serviceability, we have to consider, as I said, the deflection ability, how much the building can deflect. So with every building, we can allow the building to deflect a certain amount. So when you have wind blowing on a structure, the building itself will deflect within its serviceability limit, but it's so small that you will not see it. So when we do our design check, we have to ensure that that is being done. So what we do basically, if you are doing, for industrial building, you have to do dead load, wind load, and live load. These are the deflection limits you can consider. So L over 36 is just telling you that for dead load, you have to consider L over 36 if the roof pitch is that much, or L over 500 if the roof pitch is that much. So the biggest one, when you calculate, the biggest one of all three then becomes the governing design criteria for serviceability. Okay? I will not bore you with that, but that's what that is saying there. Okay? Any question on that? Because that's an important aspect you need to understand why we calculate ultimate load. So generally, when you have an industrial structure, you will have, when you go to bondings, for example, you will see that one part of it, the lower part of it, is precast concrete, and above is lightweight. So that actually is being done basically because of that uplift load. So that uplift load is what actually ties down the structure. So that's one aspect of that precast panel. Another aspect of that as well is for protection. So it's when you have a precast panel, that lower part of the structure, so the precast panel might go up to maybe 2.4 meters high, and then the rest becomes a lightweight cladding. So if you have forklifts in a warehouse running around, if the forklift says lost its control, it will run into the precast panel and it's still safe. But if it was a lightweight down all the way to the ground, then it can get damaged. Does that make sense? So that's why precast panels are mostly used at the lower part of the building as well. And as well, it serves as security purpose as well. So the precast panels at that lower part of the structure prevent thieves from entering the building easily. So you cannot easily break into the concrete part of the building. And if you're going to go into bondings to steal things, it's very hard if you want to have it over the panels because they are so tall. They are about a story high. So it serves those three purposes. It acts as a counterweight, it acts as a security against theft, and it also provides a rigid area for machinery working within the space. So that is why, as I said, if you have a forklift run into that side of the structure, it will not be damaged. So those are the three reasons. I think that was an exam question last year or so, or 2 years ago. Okay, so we have the portal column, which I showed you yesterday, which looks like that. For those of you who are not here, you've got a portal column, which is the column that is on the side that forms the external wall. And then you have the rafter, which connects to the portal column, and the rafter is also referred to as a portal beam, as I explained yesterday. So usually what happens is when you have the columns, we have to make sure that none of the elements in this column fail under any of the loading conditions. So that is why we have to check for every element. We check the flanges, the outer flanges, the inner flanges, make sure that the local buckling is prevented, which is why we have Doppler plates and so on. Okay, so when we're doing check, you have to check mainly what will happen when you have a taller structure like that. If you have a taller element, not a structure, a taller element like a column, and you have a lot of wind pressure, what will happen is it's likely to fail by buckling. Okay, so because it's too tall compared to its width, so it's slender, so it's likely to fail by just easily bending like that. So that's a buckling failure when it fails that way. So that becomes a criteria you need to check in the minor and major axis. Okay, when you have the guts, and as well for the rafter as well, when you have the purlins. So as I explained yesterday, you have series of guts. So assuming each of these are the guts point, you have series of guts going this way, okay, running this way. Then what will happen is that area where you have the gut connected to the flange of the column is very, very stiff because it's got a cleat plate at the back of it. Is that right? You've got a cleat plate welded and it's welded to the guts. So then it means that from one gut to the next gut to the next gut, the distance between the guts becomes the effective length for buckling. Do you know what effective length is? Oh, at least you know that. That's good. Okay, so the effective length then is taken between the guts because the guts provide restraint. As I said, the guts provide restraint. At every point, it is connected to the column and thereby preventing the buckling to happen across the entire height. So it will happen possibly between those two guts. And the same thing for the rafters as well. The rafters has got series of purlins, so thereby the effective length becomes the distance between the center to center of the purlins. So it's the same concept. So that purlin prevents the entire rafter to buckle as one, rather than to buckle in between the purlins, if that makes sense.
So how does it make sure that the structure doesn't fail before purlins and guts are installed?
Because you've got the overall capacity of the rafter member is more than enough.
Okay.
So that is the strength part that is satisfied. Okay, so for serviceability, you have to check all those local bucklings and make sure that they don't fail, which is why we have certain other elements which I'll talk about shortly. Okay, and as well, in columns, you'll have bending stresses because you have bending in the column. You have moment in the column. So you have to check for the bending stresses, you have to make sure the inside flange, which is in compression, usually restrained by fly bracing. I will explain about that shortly. The outside flange is restrained by the guts, usually, or precast panels. So sometimes what will happen is you will have somewhere else the panels go from the ground floor to the eaves level, or full panel. So in that case, what happens is if you have a column, so assuming this is a panel, and then I have a column, a big column, next to this all the way up, then that column is then tied to the precast panel at certain intervals. Have we seen that? No? You haven't seen that, right? So you don't observe when you go around. So when you have, as I'm saying, assuming this is a concrete panel, and then I have a big, I'm not saying this one, just an illustration. I have a big full-size scale column. That column is next to the panel. So I'm talking in the case where you have precast panels from ground to roof level. So in that case, what happens is you will have the panels, precast panel sitting next to the column. And that column is then connected at regular interval to the flanges. So that also prevents local buckling of the flange. And that's what that is saying. So the outside flange is restrained by the guts or precast panels, in the case you have panels. Yes, they are, because it's part of the envelope. It's load bearing. Sorry? They carry lateral and gravity load as well, because it's part of the roof sits on it. Depends how it's been built. So it just depends on the design. Sometimes you have the portal frame in. So we've got different types of, we'll talk about later. We've got precast and tilt-top construction. So they are built differently. So we'll talk about that a bit more in week 9 or 10. Okay? So similarly as well for the rafters, they are governed by strength and deflection, which I've explained. We have to ensure that they satisfy strength. So the strength means they can take the load. Serviceability means they can only deflect within certain limits without any yielding of the member or failure of the member. So that's what strength and serviceability is. Okay? So generally what we do is, which is, as I said before, that our structures around the world are always over-designed, because even though you have a yield stress, and beyond the yield stress, you've got the ultimate stress, which is the reserve strength, but we still factor the yield stress. So when we do when we check most of the time to sort of check whether our structure can take the load, we don't actually stress it up to the yield. We factor that down. So what that means is if the yield stress is 300, we factor that, say, by 0.8. So we only load it up to 250. So which means despite the yield stress is this much, we only load it up to this much. And then you've got the yield stress, and beyond that you've got the reserve strength. So you can see that our structures are mostly designed safely around the world. So that's what that is saying, looking at allowable stress design, wherein the possible maximum stress is taken as 0.66 times the yield stress. So you don't go beyond that normally for these structures. Okay? Now, I'll talk about the fly bracing, which helps to restrain our structure. Let me explain this carefully. I think I've already explained a bit of it. When you have a portal column or a rafter, what happens is you have, assuming the rafter first, you have internal pressure. Internal pressure will tend to push all the elements upwards. Or if you have a wall, it will tend to push the wall outwards. So some of that pressure will be impacted on the bottom flange of the rafter. Is that correct? So what will happen is that bottom flange is likely to fail by buckling as well. So at the top, we've got the purlins. But at the bottom, we have nothing. Is that correct? So to prevent that from happening, we then use what we refer to as fly bracings. Can you see this? That one there? So that fly bracing is connected to the purlin, and then it's connected to the bottom flange of the rafter. So that's then so that fly brace will be at intervals, will be one here, and so on. So that then prevent the entire bottom flange from buckling. Because what happens then is the effective length of the bottom flange becomes from one fly brace to the next fly brace. Just as what happens with the purlin as well. Does that make sense? He's sleeping. What happened? Coming from work? Okay? And it's the same thing as well with the columns. So when you have the columns, you have, so that's the inner part of the column, because that's where the rafter connects, the knee. So when you have the columns, what happens is that column flange will fail by buckling as well. Is that right? So to prevent that from happening, we then provide fly bracing to the inner flange, which prevents local buckling of that flange. And that fly bracing is connected to the guards as well on the wall. So when we go to site, luckily, we might see this if we're lucky enough. If we're not lucky enough, just take it for granted here. Okay, so that's what that page is saying. So top flange in compression, due to gravity load, effective length is taken between the distance of the purlins, which I've explained already. Bottom flange is in compression due to uplift when you have pressure pushing upwards, and then use fly bracing to laterally restrain the bottom flange. Does that make sense? No? So that's when you have a beam. That's what you're seeing here. You've got a beam, and then The bottom flange will get a cleat, so you got a cleat, so that's a cleat plate behind, or the gusset plate behind. And that gusset plate is then providing a point where the fly brace is tied to the rafter or the column, and then it's being tied to the purlin or the guts. It's the same way they are connected. Okay, so that's what that is saying. Sorry? What? The fly brace? No, it's bolted to the gusset plate. So there's a gusset, so you can see that gusset plate there, or cleat there. That's a gusset, not a cleat. That's a gusset plate there. It's welded to the beam. Okay, and then there is a hole in that gusset plate which receives the fly brace. Does that make sense? Okay. So that's what you're seeing here. For example, you see that's a column in this case. So you see the fly brace is connected to the guts. So that's the guts there behind the column. So the outer flange, which is that flange. So that is my column here. This is my column. This flange is the one at the back. Okay, it's like this. So that flange, the guts prevents local buckling of that flange. And the fly brace prevents local buckling of this flange, which is the inner flange. Okay? So you can see with all of these elements spaced at intervals, I think usually maybe every other second guts, or depending how the design is being done, then you can see how stiffened the entire section becomes once everything comes together. So that's what you're seeing here. So you've got a column, you've got a portal and beam, the rafter, okay? You've got the rafter and the column. So if you have at the top, the purlin spacing, so the outside column, the outside flange in compression, okay? So which means if I've got that, okay? If I've got that, which is like this, the top one, that top member, this one is this. If I have wind from outside, or load pushing inwards, then I will have this system will tend to bend this way. So that top flange be in compression. When the wind blows upwards, it pushes upwards, then this will tend to hug. Then the bottom flange will be in compression. And while it is a steel section, it will have a very, very high tensile strength. The compression capacity is not as high. So that is why the compressive capacity has to be, the compressive ability or resistance have to be augmented to ensure that it provides enough capacity to resist the loads. Because the compressive capacity of the steel that is offered by the section is smaller, particularly for local buckling. So that is why we have to ensure we have all of these things. So as you can see, if the load is like that, pushing downwards, that is in compression, that is the outside flange. In compression, the effective length becomes 0.85 multiplied by the spacing of the purlins. So SP is the purlins. That's what you see in there. So SP is the spacing of the purlin to purlin, and SF is the spacing from one fly brace to the next fly brace. Inside flange in compression, 0.85 multiplied by the spacing of the flange, of the fly brace. And if you have a column that doesn't have any guts or fly braces, then the effective height becomes 0.5 times the overall height. Is that correct? Which is what you've learned from columns design when you do materials and structure. So, what happens when we have loads on our portal frame? We have a lot of loads imposed on it. We have different action that is generated. So you have to make sure that all these loads, as I said, is resisted adequately. So when the structure is loaded, you will have moment at that point. So you can see the bending moment. When you have wind blowing, you have a lot of bending moment. The bending moment here is much bigger. So you can see the bending moment goes up to 203. And that bending moment diagram you can see is the dead load, crosswind plus internal pressure When you add all of that, it's what giving that maximum bending there of 203. Okay? And as well, so that's for the rafter. And as well, when you look at the column, for the same wind, you'll see that that wind there, DLCW plus IP, same as that, gives the highest bending at that knee connection, where the column intersects with the rafter. So what that means, it tells you that that point is the critical point on the structure. I explained that yesterday, and just rehearsing that again. So generally, the moment at the knee, so that's the knee connection when you have the column and the rafter, the moment at the knee is usually high, more than the capacity of the section here. So that section capacity is very, very small. So because we want to resist a much more bigger moment than the section capacity, we then add the hunch, which provides a deeper section where we have maximum or higher bending moment. Is that making sense? Okay? So that's the concept, and that is why we have the hunch. So the need for the hunch, maximum moment occurs at the knee. When you add that on the rafter, you have that on the knee, you have a lot of moments transfer between one column to the rafter. Then typically, just a smaller section is not enough. So what they will do, they will have the hunch. That's the hunch. So that's all is the hunch. So what will happen, they will just remove the flange of that hunch and weld that web to the flange of the standard section. So that's how the hunch is formed. Sometimes, and I think I mentioned that yesterday, I will just draw that so that you see what it looks like. Sometimes you can have a much more deeper section used for the hunch. So sometimes what will happen is if I have, can you see this? If I have my column like that, okay, assume that's my column, I will have a hunch with the end plate. So usually that will becomes an end plate. Okay. So instead of having what I've shown you like this, they will have a deeper section here, and then it will continue on with a smaller section. Is that making sense? So not all the time you will have a triangular hunch. Like the sites we are going to, this is what you see. You will see on site. They have used a much deeper section, so that's the knee. So which means instead of having a triangular cutout, they have just used this much, which is this deep one, all the way up to here. And then they reduce it at that section. Is that making sense? So that's what they've done. So you will have that in most cases. So if you look at that drawing, why I'm mentioning this, is what is that? Is that a pin or a moment connection we will form? Okay, maybe I'll put some bolts. So I've got bolt here, bolt here. What is that? Is that a pin or a moment? The reason why you need to have moment connection there, because you can see that that moment goes all the way beyond the hunch. So that is why you need to ensure that that connection or transfer from one rafter to the smaller rafter is a moment connection, if that's making sense. Okay? Is that okay? Is that clear? Any question? Okay, so that's all explained. So because of that, we've got all that deeper section, which I've just explained. Sorry? Yes. There is a plus or minus. it will have a much more labor involved, okay? But then use less material as well. Whereas the other one, you don't have to do any much labor. So it's almost comes to the same thing, I would think. It just depends on the economics. Okay, so when you have a moment connection at the knee, what you have the column, you've got the rafter, you've got the hunch. So you can see the hunch, as it says here, is 410 UB 60. And this is taken from X, means they cut out from 410 UB 60 as well. So it's the same deep beam, just that we remove the flange and tapered it to the design length there. You've got the end plate, so that's the end plate there. The first plate is the end plate for the rafter, and then that is bolted to the flange of the column. So that's the column flange there. And then what happens is when you have all these huge loads from one member to another, which I explained yesterday, if it's like that, when you have wind blowing, this structure is going to move like that. And it does move, but you don't see it because it's very, very small. Okay? It moves when you have very, very high wind. Sometimes as well, when you have gravity load, what happens is that rafter will try to do something like this. Is that correct? Will do something like this. So that is what is referred to as the closing moment at the knee, when it tries to rotate clockwise and close. So what will happen is, to prevent that from happening, I think I explained this yesterday, is to prevent that local buckling of the flange due to the large closing moment. Then we have what we refer to as a Doppler plate, which is what you're seeing there. Can you see that? Doppler plate. Okay? So that prevents the bottom cord from failing at that particular point. Similarly as well, when you have internal pressure, what happens is the column is going to be subjected, if it goes upwards, a lot of pressure pushing the roof upwards, that's just going to tend to stretch up the vertical column. But the roof rafters is going to push upwards and is going to sort of try to do something like this. Is that correct? So then in that case, it's likely to fail the top part of that column flange as well. Hence, we have Doppler plates at the top as well in some cases. It's not there in this case, but that's the reason why you'll have Doppler plates at the bottom and the top. So that's the thickening. That's as I just explained why we need that. So you have, all those tension and compression forces acting due to the opening of the knee. We then provide stiffeners. So that's the stiffeners there, stiffeners. And then the shear force usually is taken up by the bolt. And these bolts, they have got very, very high capacity in shear. So they can, having 8 bolts at the knee usually is enough. You saw the big bolt I bought the last time? That was from a knee connection site we went to 2 years ago. It's very, very big. So hopefully when we go, you'll see most of these on sites. Okay? So sometimes as well, you can have what we call a bolted knee. They are not economical, but they can be done because you'll have to use a lot of resources, a lot of material, a lot of labor if you want to have a bolted knee. So it uses less material, but then you'll have bigger sections as well. So most of the time, it requires, because you have a lot of bolts at the connection, you have to do a lot of machining, a lot of drilling, and then it becomes more laborious. So we tend to avoid them. But then you need to know that they exist as well. So when you see them, you don't say, I didn't say they exist. As you usually say, James did not say. Okay, at least I said. Okay, so look at how the structure behaves when we have loading. Is what we are looking at on this slide. So what you're seeing is, you've already seen that. So we've got the moment happening, moment happening due to closing at the knee. You've got moments when you have the internal pressure, try to push the roof upwards. You can have moments as well transfer the other way. So what happens generally is if you have the end plates of the knee or the rafter, not the knee, sorry, the end plate of the rafter and the hunch, that section, or the portal beam, then what happens is if the end plate is very, very, very thin, what will happen? It will fail like that because it's not strong enough to resist the bending. So it will just buckle and fail by buckling. So that's a local buckling failure. Whereas if the plate is very, very thick, what happens is because it's very, very thick, so it's got enough capacity, what will happen? It will tend to pull the bolt out of the connection. Can you imagine that? So the bolt will tend to fail in tension because it tends to pull it out. And these are some of the common failures you will see when you look at, very old portal frame buildings or under-designed structure. So in this case here, you've got 2 bolts or 4 bolts at that position. 2 bolts, 4 bolts at the top. How many bolts? 4. So we've got 8 bolts, is it? At that connection. So please, when you go to sites, if you look on LMS, I've already put the brief, which I will talk about shortly. There are no number of bolts given in the brief. So you have to make sure you count the number of bolts that you found on site. I never said this before and people get the assignments wrong because you lose marks for that. So when you are going to annotate your sketches, you don't just say M20 bolts. You have to say 4 M20. So please remember that, but we'll talk about that shortly. Okay? Now, similarly, you have moments if you go back to that diagram here, you will see that you've got moments as well at the, what is that called? The apex, okay? So because of that moment at the apex, hence we often need to have a moment connection at the apex. So that's the apex, which is the point where you have one rafter like this and another rafter going that way meets at the top point. So that is why you can see this is being designed as a moment connection because I've got 2 holes at the top, 2 holes at the bottom, and 4 in the middle. Can you see that? That's the end plate. So that's the end plate. So that will be another end plate here. So that end plate there is one of these. So you have another one which forms the V shape. Okay? So usually that is required because we've got moments which exist at that point. This is just showing you some calculations, but the essence is to let you understand why we have a moment connection there. So sometimes, as I said, I think you've seen this before, when you have a very, very long section, we tend to have a bolted splice. So a bolted splice is usually placed at the point where you have minimum bending moment and only shear force exists at that point. So remember your bending moment diagram where you have 0 shear force. And what happens to the bending moment? Remember that? In materials and structures. Maybe James said this time, I'm sure. You must have seen that. So bolted splices always should be placed where you have minimum bending moment. Because if you have a bolted splice, most of the time they have to be designed to only transfer shear force across the joint rather than bending. So what will happen if I go back to my bending moment diagram? So here, I've got the bending. So somewhere around, so I've got another bending here. This is the governing one, so which means this will be maximum. So at that point, around that area, would be where is the best point to put my bolted splice, where I have very close to 0 bending moment. So if you're on site as a project manager and then you have this engineer who has gone out on a Friday night, came home on a Saturday morning, does the design 12 p.m. on Saturday and send you the design and put the bolted splice where the moment is maximum, send that back to the engineer and say that is wrong. So that is the reason why you need to understand some of these things. Because it happens. Yes. Not deliberately. Probably it can be a drafting error where it's been wrongly placed. So if you know that this is, oh, I'm going to have a lot of bending here, as a manager working on site or doing these buildings, then I can say, oh, I can, the builders, of course, they do this all the time, despite engineers do all the design, but they have a lot more experience in most cases than the engineers.
But how would you know from the drawings?
How would you know? By experience. You know, for example, that...
Because the moment won't be drawn there.
Okay, say, for example, you're on site, and then the engineer sends you a drawing with that not having a moment connection. And then it just have maybe 6 flexible bolts, which you know is not going to work. Are you going to contest that?
Yeah, that's what it is.
So that's the thing. So you need to understand. So that is why when you do your materials and structures, we tell you about shear force and bending moment. You didn't do shear force and bending moment in materials and structures again? You did. Okay, you did that. When you go into the industry, you'll get what I mean. You will see a lot of mistakes, so many mistakes. Even when we were looking at the drawings, Jenjen and I, when we were looking at the drawings that we're going to the site, we spotted a few mistakes already on the drawings. But, you know, maybe they have picked that on site and they have corrected it. Okay? So, generally, when you have a bolted splice, it's much easier if it's a beam. Usually, if you have ways and means to make the constructability easier or buildability much more easier, it's always better to do that. That is why in this case, for example, I explained this before, we have the plate welded to one side, so what happens is when you put the other beam, this plate picks up the beam and you can bolt the connection easier. And this is just thinking about how it's been constructed, which not all engineers generally do. So before I'll give you a break, I'll go a couple of slides more. When we look at the columns, so this is the base. The columns, that column will have a plate, which is called a base plate. That is called an end plate. Remember that? That's an end plate. But for the columns, you will have a base plate. And sometimes when you have the columns, you have a member sitting on it. You will have a plate at the top, and that plate is called a cap plate. So you have a cap plate which sits at the top, you have a base plate which sits at the bottom, and then you have an end plate which sits at the end of a member. Okay? So in this case, we've got a base plate here, okay? And then it's been tied down into the foundations, into the footing, sorry. So you tie that down using, as you can see in this case, 8 high-strength bolts and a thick base plate. So usually what will happen is those bolts, okay, these bolts, which are usually threaded rods, they come as threaded rods, is set as a cage and put into the footing so that, I'll show you that in the next slide, so that when you pour the concrete, it doesn't move, okay? So what we are looking at here, let's look at the behavior first. You've got a moment connection, fix, and a pin connection. This is very expensive, this is very cheap. Most of the time at the base, we only need to ensure that the column is held in place and vertically plumb, as it says there. It stands vertically. So most of the time, 2 bolts is enough, but we don't use 2 bolts. You have to use 4 bolts minimum for the base plates to have a pin connection. Now, when that is placed, that is been set, you put that, and then you concrete the footing, and then later on you put your column over, and that column, as you can see, does not sit directly on the footings. Why? Why do you think that is the case? Not, oh goodness, not really. Tolerance, yes, you allow tolerance. Correct. Because why? If you put that directly on the, so if I put that directly here, and then it's not plumb, what happens? It's not vertical. Then you're in trouble. So that is why it's always, the design will be to have packers underneath the base plate. So there will be packers under there, which sit like there'll be maybe rounded, like shims, but rounded ones, which is sit over the threaded rods. and then that is used to adjust the verticality of the column, and then you then put a non-shrinking grout under the base plate. Unfortunately, you will not be able to see this because they have already finished all the structure, so you will not be seeing that. But you will see definitely the grout. So that underneath is the non-shrink grout. So that grout is put under the base plate and it doesn't shrink at all. Okay? So that's what a fixed moment is, a fixed base. Why is that fixed? Why is that fixed? Why does it say the column there is fixed? Why? Yes, it does exist moments, of course, but why? From the drawings. Exactly, because the bolts goes out beyond the flanges. So which means that is meant to take moment. So what happens is, if I push that column over, it's going to transfer bending across that base. So these are some of the exam questions. So the exam is not that difficult, it's just tricky. Okay, so now let's look at this, then where are we going? Okay, let's look at this and I'll give you a quick break. So the base plate, as I said, what happens is when you have the threaded rod, so those rods, as you saw in the previous slides, you have them like this, 4 of them. It's going to be very hard to position them one by one. So what usually happens, they come in a cage like this, wherein they use like stirrups in some cases and do tack weld them together. So this is already plumbed off site. So when you come to site, it's less labor work to be done on site. You put that in place, you concrete it, and then you take your formwork out if there is formwork, or it sits in the ground, and then you have that vertically, easily, you know it's in a perfect position. And when you do this on site in a cage, it ensures that the center to center is accurately done as well. So that's why you don't want to do this on site. Okay? So, of course, the footings generally, as it says there, which I've already explained, they also provide weight as part of the uplift capacity of the building. Because the footings are very, very heavy. So what that means is you have your columns into the base plate, down to the footing, tie down. So those footings which are under the ground also provide some uplift resistance as well, if that makes sense. Okay? So that is why we have to make sure that our footings work under, not just gravity load, but also against uplift. Okay? Most of the time, we use pad footings in our buildings. In most cases, we don't consider the bearing pressure or bearing failure is considered as part of the design, but in an industrial structure where we have a lot of pads, then most of the time the bearing capacity will not become an issue, most often. And that will depend on few sort of criteria. If you're building on a very, very bad soil, then in some cases you have to have piles into the ground. So this one we're going to, I'm actually not sure what they have used, but the drawings have got pads and pile option, which means it's not a good site. And if they've used piles, generally it's not a good site. If you've used pad, then it might mean it's a much more better site. I'll finish the footing pad and I'll give you a short, quick break. Sometimes, as you can see, when you have a pad, in some cases you will have what we call a pedestal. So a pedestal is just a projection out of the pad where the column will sit. So it's there. So that's on plan. You're looking at it on plan. When you look at it on plan, that's the footing. And then that's the pedestal where the column will sit. In some cases, you do that. And then that is how most often you have the detail for the pedestal there. Okay? All right, we'll take a short break there, and then we'll come back and continue. I'll need to finish this quickly, then I'll talk to you about the assignment. Any questions before you go? Just a 2-minute break, guys. LMS. How does this make sound?
Click here. Oh, it is extra.
It's on the computer, I see.
It should be the sound.
And the sound is not.
Are you sure there's sound in the video? Are you sure there's a sound?
I'm not sure.
I don't think. Try another video. I don't think there's any sound.
Oh, okay.
But check with the other videos because it's not really.
Yeah, there's no sound. This one has got sound. Thank you. All right, come back, guys. Let's go. You have to go early. Remember, you have to go for your class. Come, let's finish this quickly. We have to talk about the assignment. What's the question? Ask me. Don't ask her. What about if she's telling you the wrong thing? Okay, let's make a start again. So as I've said, come, quick. You guys have to go soon. As I've said before, the fly brace is meant to, we've got fly braces to help with buckling of the flanges, and then that reduces the overall effective length of the bottom flange of the rafter and the inside flange of the column. Okay? So generally, when we do the design, we have to take what we refer to as 2.5% of the maximum compressive force, which you don't need to be bothered with. So the flanges usually are like that. Sometimes you have a single one based on the design. Sometimes you have a double one. Okay? So as I say, that has got a cleat plate. In that case, there, it's got a cleat, which comes up and sort of pick up the purlin. And then that will also have a cleat, a gusset that comes at that corner, and then like that, and then it picks up by the purlin as well. And remember, I explained yesterday that you always have to ensure this one is a joint. So you've got a purlin here being joined. The purlin joint, where it's joined, always have to be over the rafter. And the same thing as well for the guards. Where there is a joint, where there is a lap between the two guards, it always has to be where you have the columns. Okay? So you've got most of the time when you look at the purlin, you've got two holes, because when you join it, you have to have two holes. So most often you always have to put the fly brace to the lower hole, always, not the top one. So if that is going to move, it doesn't sort of buckles against the bolt. That is why we use most often the bottom hole. Okay. Now, I explained yesterday about the portal frame. I used the struct this classroom. I said we've got a portal frame at the end. We've got one here, one where the column is, one where the next aisle is, and the end wall. But usually, in an actual portal frame structure, the end walls are different from all the internal ones. Always. Sorry? Now there's a reason, because if you go back to the very first slide, what's going on? So if I go back to that very first slide where I showed this, when you have that, you've got a braced end at the top, which I'll show you shortly. You've got wind load in the crosswind direction will be resisted by these walls. And wind load in this direction, most of that will be transferred to the longitudinal walls. So when you have wind on any, just a general concept, if you have wind, I'll use your phone please. If I have wind blowing this way, the walls here provide bracing support to these walls. Is that correct? Just common, general concept. So always the walls perpendicular to the direction of the wall provide lateral support. And that is why bracing is provided the way they are provided in buildings. Okay? So when you have the end, okay, the end wall usually is not a portal frame, because it has got a lot more members in it as just being a portal frame. So when you go to site, you will see that, because we're going to see a naked structure. So the end one and the end one will be one that is built differently than having a portal frame that's got a portal column and a rafter and a portal column in the middle and so on. Because these are the ends. So if you have a lot more members in there, it doesn't matter, if that makes sense. Okay? So what happens is, when you have that end wall there, provide lateral resistance to the longitudinal wall, where you have crosswind, which goes inside here along this plane. So in the end wall, you will have a lot more vertical members, and then you will have a smaller rafter spanning between one column to the next column to the next column. Is there a slide on that? There's no slide on that. How come? That's weird. There should be a slide on that shows the mullions and so on. Okay. So as I said, usually, as in this case, So if you have a standard or a typical portal frame, it will, assuming it's 19.5 meters, it will have a portal column, a rafter, and a column. But the end walls usually will have more vertical members in there. Okay? And those vertical members, referred to as the columns, are usually referred to as the mullions. That's what I'm saying. I wonder why it's not here. I don't know what happened. I might maybe find that's a page which has got all the terminologies and put it for you on LMS. Okay, so you'll have the vertical columns. You've got a column, portal column, the internal columns, usually for the end walls, are referred to as mullions. Okay? And that end wall, as it says there, the end rafter, is supported between the internal columns. So you'll have a column here, which breaks the span. So which means at the end, where you don't need the portal action, you will then have a much more smaller rafter. So what I'm trying to explain this is when you look at your assignment question, there is a question for you to show what the geometry of the end wall is when we go to site. And you will see that the sections on that wall is usually much more smaller. And the reason why we need to have those internal more columns is because we need to provide more bracing in those walls, if you remember that. Because as I said, when you have wind blowing, okay, if I borrow your phone, when you have wind blowing this way, this will tend to push over. So the walls perpendicular to that wall is providing lateral stability to that wall. That's how the design has been done, and that's how the construction has been done. So those end walls, thank you, will need those X bracing. And for that X bracing to work, it can't go 20 meters or 30 meters apart. So it needs to be broken down into a smaller span. Hence the reason why we have more internal columns, which are the mullions, which is what we learned in construction of buildings. So it's the same thing. Does that make sense? That explains it. So that is why when you go to site, you will see that the geometry of the end wall has got a lot more columns, and at the same time, the internal portals has just got a few columns. And because the end, when you go to site, you see that it's fully braced, and it has to ensure that it provides lateral stability to the longitudinal walls. Okay? That talks about nodal load, which is not quite relevant to you, so I'll leave that out.
Every section you can brace, not just which.
It depends on the design. That depends on how the design. Sometimes if you have maybe 1, 2, 3, 4, 5, they'll brace bay 1, bay 3, bay 5, and 2 and 4 is not braced. Okay, so I haven't seen much of the photos. I can't see anything on near map, so when we go to site, we'll see. So now at the eaves level of the building, when you have the column and the rafter, at that level here, you've got the eaves. Is that right? At the top level where you have the eaves, you will have an eave strut which sits in here. You will have a fascia purlin as well, if you remember. I explained that yesterday. And then at that particular point as well, you will have what we refer to as an eaves tie. So an eaves tie usually is provided between one portal frame to the next portal frame, which provides support for the guards, if that makes sense. Hopefully, when we go to site, we'll see these things. It's hard to imagine when you see me gesticulating all the time. Is that right? Very, very hard. So, sorry? Eaves and girth. Yes, that's what I'm explaining now on that slide. So you've got, no, I'm not talking, not the eaves, the eaves tie. Is that terminology called the eaves tie or strut. So it's the same, usually perpendicular or parallel to the struts. So it runs, we've got an eaves strut, you've got an internal strut goes on, but at the end you've got an eaves strut. So behind the eaves strut usually you will have an eaves tie at the eaves level. So I'm what you're seeing here is one portal frame. There is one portal frame, and then you've got an eaves tie there at the top. And that eaves tie, as you can see, it says to transfer wind load acting on the end frame of the structure or wind load at the angle of the sides of the structure. So what you see here, that is not shown here either. So it will be at that level where it connects one frame to the next frame, and then it's usually used to provide support for the guts, because the gut goes this way, so it's provide vertical support where it's been sort of provide like a, it acts as an anchor where the guts just hang on, moving down. So it's been sort of tied. So usually the bridging will be tied to the eaves tie in most cases. As I said, it's very hard to explain, especially this particular slide. But when we go to site, hopefully we might be able to see that. So it got the function there, transfer wind load, because it provides, it's horizontal and it provides restraint between the frames. And then it's got a secondary function to support the guts on the wall cladding, which is what I've just explained. So most of the time, it might be maybe of a bigger section. Sometimes engineers don't use it. Sometimes it depends on how the engineer does their design. Sometimes they'll provide a much more bigger eaves strut and ignore the eaves tie. Sometimes the eaves tie is only provided along the end walls, where you have the end walls. So that is connected. So that will be connected from one column to another. And then it supports the cladding, the guts, which supports the cladding behind it. Does that make sense? Quickly. We have another 5 minutes and then we go to the assignment. So as I explained yesterday, most of the time you will have different kinds of roof bracing. The most efficient roof bracing is to have two ends brace. So the roof bracing usually has to be braced. You have a wind brace at the top. So wind brace, roof brace is the same thing. And then you have the wall bracing, which goes down to the ground. So wherever you've got, when you're doing these structures, when you're building them, if you have a roof brace or a wind brace at the roof level, you must have a wall brace within the same bay as well, if that makes sense. So like this here, see, that one is brace, brace, brace. You definitely need to have that so that the load is taken to the ground. Otherwise, if that is not provided, tell the engineer he is wrong. See where experience comes in, is it? Okay? So normally, as I explained, if you have that been braced, then you will have the eaves strut there. You'll have internal strut. Generally, you don't need to have struts at every other portal frame. What we rely on to transfer, when wind blows this way, we then rely on the purlins to transfer the load and hold all the portal frames, these three here together, by transferring the load along their axis all the way to the next end where the bracing is and taken down to the ground. Does that make sense? So that's how the structure behaves. So wind blows this way, okay, it pushes against this, all that is braced, that load is transferred to the other end by the diaphragm action of the purlin and the roofing sheet, all the way to the other end. So that's what all of that is explaining. So by means of the bracing system, the force on the upper half of the walls are transferred to the side walls and ends to the footing and the ground. So if you have two ends brace, wind load shared between braced bays, and the purlins are usually sufficient to brace internal rafters. So no intermediate struts will be required. So you don't need intermediate struts as we have here. You don't need all of those struts. We just rely on the action of the purlins. That's what that is saying here. So you see, all of these are taken out. So you brace that, wall bracing. But if you have just a single brace in the middle, then you need to take the loads from one side to the other. So in that case, you will then have to, because this is not braced, you will then have to provide bracing struts at every other bay. So this is one portal, one portal, one portal, one portal. So these are end portal, end wall frame. This is a portal frame, and then you have the end wall frame. So if you want to have just one brace in the middle, then you then have to provide all these other struts. So then you can see you're going to use more material, and more material means more weight on the structure. More weight means bigger footings. So you can see just a trade-off. Okay? So you can have two braces as well. I think I explained this yesterday. Sometimes when the structure is so big, like the one you're going to, just bracing it over one bay is not enough. So you have to go to the second bay. So what happens is you brace from one point to the rafter, and then that bracing goes all the way to the second bay. So this is one bay, this is the second bay. So this is braced over two bays. That's what that is saying. So double bay diagonal bracing at a roof level. You then have to provide that continuous bracing member goes all the way to the other end. Most times we use equal angles to do the bracing. Sometimes we use the round circular rod to do the bracing. So that all depends on what the engineer has designed. The rest there you can easily read. Okay? And that's similar to what I've just explained. What I want to bring to your attention here when you build the structures is looking at where the bracing sits at the roof level. So what happens is that bracing usually gets tied to, that's the beam or the rafter, okay? That bracing will have a cleat that comes off from the rafter, and that cleat is where the roof bracing is tied to. To ensure efficiency of your structure, it's always good to have that bracing as close as possible to the purlin. Because the reason being, when you have the roof structure, you've got the roof beams, you've got the roof bracing, over the purlins, you've got the roof cladding, which is the roofing sheet. So all of that provide diaphragm action at the roof level. So if the bracing is lower down, then you're going to have some eccentricity between the actions of the different members, which you don't want. So to prevent that, it's best to put the roof bracing as close as possible to where you have the purlins. And I think that's what that is saying. Okay? I think I've already explained about the purlins there. Now, in the roof bracing, normally you can use different connections. So these are some of the connections you can use. You can have that welded, so you can have a plate welded like that. If you're using a circular bar, for example, circular bars are usually difficult to join, which I explained, I think, 2 weeks ago or last week, I can't remember. So normally, if you're using a circular bar, there are different ways in which you can join them. So normally when you are providing the connections, you can have a welded connection with a cleat plate, and then you have bolts, or you can have a cleat plate like that, and then you have that welded at times. So you can have different layouts like that, and that all just depends. The most important thing that we tend to do as engineers is to make sure that the line of action of the bracing intersects at the same centroid of the main member. Because if that does not happen, it means you will have eccentric load, in essence. So that is why, you see, this one, the force acting on that member goes this way. This one, the force acting on that member goes this way. And all of that should be sort of built to perfection to ensure that the center of that cleat plate is where the two intersect exactly. So that eliminates eccentric load acting on the plates. Because if you have eccentric load acting, then that cleat plate might tend to get deteriorated over time, and then maybe the welding or the bolt connection will damage. So to eliminate that, you have to ensure that those connections are properly made. So that's the same thing here as well. If you have a connection like that, what we're trying to ensure is that the line of action of the two forces intersect at the centroid of that member. Okay? So you can have, if you have a circular section, you can have them flatten out like that. to form a connection. So you see the end is flattened. So this is circular section, a CHS. They are very difficult to join. So you can flatten the end, or you can have a welded T to them. So that's a welded T end where you've got a circular section, and then you create a T end using two unequal angles, welded to form like a cap plate. Okay, which is that. So that is that. That's just the plan. This is the elevation. That's just the plan. This is the elevation of that. Okay. So some more connections for you. Sometimes when you have CHS, crossing each other, it's very difficult for them to join. And what you, as I said, you have to also ensure that the line of action of the forces intersects with the center of gravity of the connection. So to ensure that, you have to make sure that that crossover between two bracing member is brought to a minimum. So to ensure that, sometimes, as you can see, in this case, you can see here I've got a circular section. If I want to use another circular section this way, then the line of action is going to be different at different levels. Is that correct? So if I assume this is a circular section, one goes this way, one goes this way. So the line of action of this will be higher than this one. So to prevent that from happening, what normally happens is this is circular in shape. So what you can do, you can weld a cleat plate to the side, and then you connect the other one. So they all become or sit at the same level, which is what you're seeing there. That's what you're seeing there at a typical intersection. Or the best one to use is what we call an intersection ring. So that intersection ring provides every member to be acting at the same plane. And then that way, eccentric loads are eliminated, which is what you want to have. Zero eccentricity in your structure, because when you have an eccentric load, that force acting multiplied by that eccentricity generates a moment. And if you don't account for that moment, it can be acting on your structure and can sort of impose additional load that is not accounted for. So that is why we need to sort of understand how these work. So usually if you are a project manager, the engineer does a design and use, say, a 162 CHS, which is really, really big, 162, crossover, call the engineer and tell them that doesn't work because of it's not efficient. You're going to have eccentric out of balance moments at your connections, and that is not good for your structure. And that's why the intersection ring is really, really a good one. Okay? Any question? That's the last slide. Any questions on that? So that's all relatively straightforward and simple, I would think. Do you have any questions? No? Yes? You still happy? That's good. What about you? Any questions, guys? So now let's go quickly to the assignments. I don't need much time on that. I just want to tell you what the rules are, and you can go for your next class. I've opened the assignment up just then. That's one. So if you go to your LMS, assignment 2 is on LMS. Similar to assignment 1, it's a group assignment. And the reason why we do group assignments in this subject, because it's a subject that teaches construction, and construction is not a one-man's job, it's a teamwork. And that's part of the attributes you have to fulfill. So assignment 2 is on what we call a steel portal frame building. Is it in this class? Yeah. Oh. I was worried I saw him coming. Can you see this clearly? Yes? No? Too small? I'll go to one side first so you can see. That's better? So as it says there, it's 2 students to a group. The only rules in grouping is you have to be in the same tutorial, that's all. That's the only rules in the assignment. Okay? So for you to be able to do this assignment, you need to come to site. That is why the site visit is compulsory. Because why? If you come to site and you're in a group with the other students, and then you're going to depend on the other students to do all the assignments. If you don't come to site, you're going to do this assignment. It's very, very difficult. So when you go to site, what we're going to do, we're going to site next Monday, and we're going to gather all the information you need. So there are some questions you can answer on site. So I will advise you, if you want to make this is very much more of a simple assignment. What you can do is, as with your group partner, you start preparing for the assignment before you go to site. Because when you go to site, it makes it easier as to how you tackle the questions. Because some of the questions you can actually already answer before you go to site. So you can make your sketches and so on. So there is a question, for example, say what the base plate looks like. So you can, virtually draw a column, put a base plate, and then when you go to site, you just say this is 6M12 or 6. So the M12 or M24, M32 is already given to you, but the numbers of bolts are not given to you. That's why I said when you go to site, you please make sure that you take note of the number of bolts. So if you look at the brief in the other additional data sheet, which I will show you shortly, that is not there. So the technical data attached, which is the next sheet I'll show you shortly, provided together with your site observation, photographs, explanation, and site knowledge of portal frame design. You then use that to answer the questions. So it's very, very relatively simple. Okay? So I'll give the tutors sample of assignments to show you, very good ones. I think last year I got somebody who got 98, which was really good. So if you get the marks, we give them to you. 98? Yes, it was that good. Yes, it's possible. Why you think it's not possible? It is possible. Okay, Leo, who knows Leo? Leo is in year 3 now as well. He got very good marks in this assignment. Okay, so what you're going to do, you're going to do a report. It's not like year 12 assignment. It's a professional report, so it should be well presented. And when you're presenting your report, it's better to bind it, have it bound, with the ring binder, than just staple it. Because presentation, goes a long way when the teachers are doing the marking. So what you have to do is to make sure that your answers cover everything that is asked of in the why this is not moving? Maybe because I've zoomed it. So I will zoom out again. There are 16 questions. So they are very, very short questions. Usually it's about a page to a question. So it's very, very straightforward. And that page includes brief description, includes photos, includes annotations, and identification of elements. So it's very, very straightforward. So for example, the first one, of course, it's general. Remember, this is 20%, so it's a bit of work as well required. It's 20% of your assessment. Question 5 says, provide a detailed rule drawing, annotated or annotated photograph of the rafter to typical internal column connection. So you see how easy it is? So for you to do that, you have to go to site, you have to know how the connection is done, and then you do that and get maybe 1.5 marks out of, because there are 16 questions. So these are the sort of questions. Question 6, are there internal columns designed to take bending or axial load, or a combination of axial and bending? Based on your site observation, use annotated sketches to explain. So you see, if you don't go to site, you will not be able to tell whether it takes bending or not. So, and I can't tell you, unfortunately. Okay? Does that make sense? So that's the assignment detail. Now, in the assignment, there is no rule to say you do question 1 to 8, you do question 9 to 16. It's a group assignment, and it's the responsibility of you. If you are separating the questions, that's fine, but that's not how it's submitted. It's submitted as one assignment from 2 students. Okay, so if you separate the work, it means if someone go and do bad work and you do the good part, it's going to affect your marks. So it's your responsibility as a student to check if that's the way you're doing it. The best way to do it is to do it question by question, the two of you. That's where you learn as well as you go along. That makes it easier, rather than separating the questions. Okay? Any question on that? So that's just the assignment questions and then the rules. Now, the submission date is when? On the 10th of October. So now, submission for this assignment is 20% to the report. So that's 20%. If it's 20%, if you get 19 over 20, both of you get the same marks. There is no separate section that you have 18 and this will have 19. So that's why I'm saying that you check each other's work thoroughly before you submit. So based on the questions, we have approximated that you will have about 22 to 24 pages max. So that includes the cover page, the title, the lead page, table of contents, if you have references, because there are 16 questions. And as I said, it is about one question to a page, normally. And it's not, this is not about writing, guys. Read the question, you understand the question. It's more about telling us what your findings is on site. So it's about going to site, understand how the structure is built, and Peter and I and the project manager will be there. We'll be splitting into groups and we'll explain to you what we found on site or how the structure is being built when we go to site. So that's what I'm saying. If you don't come to the site, you're not going to have any way of completing the assignment. So as it says there, all students will share the same mark. I've explained that. And the drawings should be done in A4 as required or A3 and folded. Okay? And as it says there, use note form only in your report. This is not a literature assignment that you have to write an essay. It's, dot point, bullet point, very short, brief, to the point. It's a technical report, and it's not meant for the lawyers to read. It's meant for managers to read, construction managers, not the lawyers. Okay? Now, what I will advise is to make sure that you've answered all the questions. That's why I've put that in. All the questions should start on a new page. So don't write half a page and then you start question 5 on the same page as where question 4 ends. Now, to supplement what you're doing for your assignment, you've got to use this sheet. So there is another sheet given to you which is called additional detail sheet. This one. So what we've done for you, make it very easier. You see how good I am to you guys? I've made the work so easier for you. I've separated everything into portal frame. So portal frame means all of what you see in there deals with all the properties of the portal frame. Does that make sense? So we've got a portal frame, we've got the footings. Is there a footing section? So we've got the roof and wall elements, so all the struts, the connections, the footings, everything is separated for you to answer all the questions. So let's go through a couple of them quickly. So for the portal frame, so firstly the properties of the building, as you can see, the building, the overall dimension is 303 meters by 114 meters wide. So it's really massive. And the precast panels that will be used are 150 thick and they are 2.1 meters high. So that's what I was saying. And then, so what happens is they have built from ground to 2.1 meters precast, and then above that they have used color bond cladding, which is what we've gone through. Okay? Now the portal frames, you see how far they are spaced. Portal frame spans, 114, and then each base are at 10.25 meters. So which means from one portal frame to the next is 10.25, to the next is 10.25, to the next is 10.25. Is that it? Yeah. Oh, sorry, the end bay. Sorry. I'll go back again. I'll take that and I'll start again. So that's for the end base. So the end base, maybe I need to explain that to you guys so you understand what that means. Can we see this? Oh, sorry. I'll put this. The guys who are not here, they will not see this. So put this on the screen that is not recorded. So that's one is the one that's recorded. So when they stay at home, they will see the lecture notes. Can you see all of that? Yes. So that's 303 and that's 114. Okay? So 303, you've got the end frame. So between the end wall frame and the portal frame and the portal frame and all of these. So it goes, and then you have the last one. So the first one, from here to here, this one is the end bay. Does that make sense? And then all other interior frames are at 11. So this one, it says is 10.25, and the next one all the way to here is 11.3. So all of this is 11.3, 11.3, all of this, and this last one as well, which is the end bay. So you've got an end bay here, an end bay here is 10.25. Yes? That is a center-to-center dimension. So when you're doing your layout of your structure, I've already answered one question for you. So that's the benefit of coming to class. Don't take a photo of that. Does that make sense, guys? So that's what that is saying. And then the external columns are already given, blah, blah, blah. And now, this section here is fly bracing, purlins, guards, and so on. And then you've got the struts. So now, quickly, before you go, you look at the struts. You see, you've got the eave strut. The eave strut is 219 by 6.4 CHS. And then the first interior strut goes over 2 bays. It's 219, the same diameter, but different wall thickness. So it's 4.8 CHS. So when you look at the connections, for example, you see it says it's got 6 continuous fillet weld and M24 bolts. But I don't know how many bolts are there, unfortunately. You have the drawings. You will be in trouble.
You should have told me before. I would have taken a copy. I haven't taken.
Yes, I know, because that's why I stood there and I took them from you. Because he printed them for me in his office. Okay? So that's the information you need, guys, and it will be much more easier when we go to site and have a look. Note the rest, observe on site. So if you look at the footings, now there's something I need to tell you as well. Because some of the elements, they have used different elements. So like the footings, they have got different pads, but I've just given you one size. So just take all as the same size. So they've got footings goes up to 2.7 square as well. So they've got 1.5, they've got 1.8, 2.1, 2.7. But the most common one was 1.8, so I took 1.8 square. So when you go to site, if you see that, just ignore. Just assume. So there are so many other elements that are different, but I've just taken standard ones. Is that good? Any question? All happy? It will be easy. This is you will see, it's a much easier assignment. Otherwise, I will see you on Monday. Please make sure you come on time for the site visit.
Is it this Monday?
Yes, next Monday. Yes.